Thank you all for coming and being brave enough to stay until this late. So I'm going to be talking about geometric measures. It's based on a sequence of papers, joint work with Ziv Bar Yosef, Ravi Kumar, and D. Sumikumar while we were all together at IBM, and since then they decided to pursue greener pastures, literally. Alex Andoni, who's here, David Woodruff, who's my colleague at IBM Almaden, and Mihai Pătrăscu, who sadly is not with us anymore, and I would dedicate this talk to him. So what is information complexity? So we have seen in this workshop information complexity being used to address the different kinds of problems, starting from classical communication complexity, say the two-party case, to multiple parties, number in hand, as well as so add streaming models, for example. So it's really hard to pin down a mathematical definition of information complexity, and perhaps there is none. But nevertheless, we can agree with this, that you know it when you see it, and I'll let you Google this and find out in what context this was said. Okay, so, but here sort of maybe a first cut definition at information complexity. It's still not mathematical, but it demonstrates the limitations of computational models by bounding the flow of information. By some stretch of imagination, you can also think that this applies to the extended formulations where people wanted to lower bound the size of these LPs. So in any case, if any of you decides to write a monograph or a survey, please quote me on this. So Alice and Bob, okay, this is the last, fifth day of the workshop. Alice and Bob have been talking for a very long time. I mean, Bob has been talking, but Alice, my God, she's been just talking and talking more often than Bob. So if you are like me, who came to US in the 90s and was, looking into see what does American culture represent, so probably for some of you, your world was defined by the TV show Seinfeld. So perhaps you're thinking what happened in one of these episodes. It's the famous episode in which the phrase, "the worlds are colliding," were uttered. It's a very good episode. And so this is a conversation between Elaine and Susan. So yeah, so Elaine wants Susan to join her, but she says, all you guys ever do is talk and talk and talk. And okay, so that's what Alice and Bob have been doing. I'll give you a few seconds to read it. So, okay, so, right. So we have, at this point, Alice and Bob are tired, and then perhaps they're talking gibberish. You just want them to, may the gods of information theory forgive me, we want them to shut up, okay? But no, actually what's happening really is that they are actually conveying some information to each other, but it's much less than 1 bit, okay? What could possibly be interesting about that, right? And I think for those people who are familiar with these things, this is not a very surprising thing. So you can imagine the following situation where it has been applied repeatedly. Alice and Bob use very few bits of communication. This is now bits of communication to solve a particular problem. And you want to show that this is not possible. So that this implies in many cases, direct sum or whatever, that they can actually solve a sub-problem in which they manage to convey less than 1 bit of information. So that happens, okay? But actually we want to show that this is impossible. So we want to prove lower bounds in this setting, and what I hope to show is that this can be done. This is certainly one way to proceed. Using the geometry of communication protocols. So you have seen in this workshop information complexity being used to being applied to study problems about geometry. In these extended formulations. But here I'm saying that I want to study use geometric measures and tools to prove lower bounds for information complexity. So the motivation for me to give this talk, and by the way, all these results are were proved in the last 10 years, so there's no recent results here. But my motivation for giving this talk is that usually when I give a talk on this direct sum thing, I start with, okay, the big machinery, information complexity, do a direct sum simulation, blah, blah, blah. And then you get to the part where you want to prove this information complexity of this small problem, less than 1 bit, but nevertheless interesting. But then you think, oh, actually, I'll just throw something at it and it will work. And I don't really need all this geometry stuff, okay? Perhaps some of you believed this at one point, probably still do. So if you do, then you can leave this talk. You don't have to stay here, and then I'll know who you are. And I also believed it at one point. But I think that there is something interesting going on here, and this talk is an attempt to sort of maybe resurrect that thing, that we should study this geometry more. So I'll be, for those of you who have seen these types of things, this is more of like, a rehash of things, but for some of you it may be things that you have not seen, because you never get to look at that part in most of the presentations at least. So, okay, so it's going to be a lightweight talk. I originally thought I was the last speaker, so I would just finish early and you guys will be happy with me, but maybe I can ramble on like this and fill the time. Okay. Okay, so good. So let me start by describing how we get to this geometry. So this is the notion of a transcript wave function, a fancy name for something very, very simple. So when you have a particular protocol, you can then say pi, and I'm studying only the two-party setting for now, that pi of xy is the probability distribution, this ought to work, over transcripts on input pi on an xy, on a particular input xy. So the coordinate corresponding to tau represents the probability that the transcript equals tau. So this is a vector that lies in the unit simplex, so the sum of these values is 1. But it's not such an interesting geometry there in the L1 space, and we know a far richer thing when we move to the L2 space. So how do we actually do this? So we take each of these probabilities and just take their square root. So that just moves it from the unit simplex to the unit sphere, particularly in the positive orthant. So now we have some geometry that we can study with this, and that's essentially this notion of Hellinger distance, which basically is a scaled version of the Euclidean distance between the transcript wave functions. The name was an attempt to appeal to the quantum folks. I don't know if I succeeded. The sum of the squares of these things is 1. So the Hellinger distance is basically the L2 distance, the Euclidean distance between these two transcript wave functions, scaled by a particular parameters to make sure that it's always between 0 and 1. And so it just seems like a notational switch, but I actually want to think in these terms because I think it helps us also to build better notions. That is, that I want to think of this as actually defining a new distance, not a distance between inputs. So you have two inputs, x, y, x prime, y prime. I'm actually using this distance between the transcript wave functions to say that this is the distance, real distance between these 2 points. Okay.
The wave functions are defined with respect to a particular protocol, right?
Yes, the protocol is fixed.
On the left-hand side, those are actually inputs.
Yes, so these are inputs, and I'm inducing some kind of distance between them based on a fixed protocol. The protocol defines that distance. So a different protocol would define a different distance, right? So I am not going across protocols. I'm just looking at the geometry of this for a fixed protocol. Okay, so because this is now, and this is true even in the L1 space, but now we are in the L2 space, and also it's still they induce a metric on the input space. So you get things like triangle inequality, which is nice to work with. So that's already some kind of geometry. But a far more interesting geometry you get when you actually look at the square of this distance, the Euclidean distance. And this leads to some very interesting theory. The square of the Euclidean distance belongs to this class of distance spaces. It's a distance space, not a metric space, called a negative type distance space. A classic reference for this is Diza and Laurent. And it plays a very important role in the theory of metric embeddings. And so there are lots of interesting theorems that one can show here in this theory. I mean, there's Schoenberg's theorem, which is one of the classics in this area. But you can even get quite a bit with simple theorems, so for our purposes. And this is one reason I believe that we've really sort of scratched the surface, because we are able to do already so much with these simple types of things. So this inequality says that, if you have a bunch of coefficients that sum up to 0, then this inequality always holds for any set of vectors, the VIs. Okay. All right. So consequences of this are you get, nice inequalities. So my convention is that in these inequalities, the bigger side will be denoted by red, and the smaller side will be denoted by blue, to the extent I can stay with this convention. So this star inequality says that if you sum up the red edges, and by what I mean by that is take the distance squared, then it's greater than or equal to the sum of the blue edges. And so this is the star inequality, the 5 here. Oh, so there is a constant that we'll have to put here. If there are S vertices here, then you would put 1 over S. This other thing is something, so on a quadrilateral, it says that the 4 edges, the sum of them is at least the sum of the blue edges. This is also called the short diagonals lemma. And this already has a very interesting consequence that the Hamming cube in 2 dimensions cannot be embedded isometrically into the Euclidean space. And once you then a proof by induction, basically you take these inequalities, the proposition gives a particular type of inequality, and then you look at the cone of all these inequalities, and one such inequality in this cone would be the thing that says that the Hamming cube in n dimensions does not isometrically embed into Euclidean space, and in fact it suffers a significant amount of distortion. So that's a result due to n flow, but it has a simple proof using these types of inequalities. Okay, and this will be these two. I illustrated these two because they show up in information complexity as well. Okay, so far, okay, so we know that this negative type space, you get a rich class of inequalities, and I want to say that, fine, we also get additional properties, because we are dealing with the transcript wave functions induced by particular protocols. So, and these properties will come purely by the rectangular structure of protocols, which has been referred to, which you have seen in some of the earlier talks. So one of these is the Z lemma, which says that this diagonal is at least the sum of these 2 blue things, and probably half the sum of these 2 blue things. And this other X lemma, which says that actually these 2 diagonals are actually equal. So I want to emphasize that these are not properties that you would get from any particular embedding. They are the embedding coming from communication protocols. Okay, so of course the point is that when you look at these types of inequalities, there's just some labels, some bunch of points. Some of them are called as red edges, and some of them are called as blue edges. It's more interesting if you can actually associate some kind of meaning with these particular, things that are being connected by blue edges and things that are being connected by red edges. And that comes from looking at particular metric spaces. So I want to tell you something about inequalities that come from metric spaces, and that connects to this, that was motivated by looking at this following problem, which is the two-party communication problem, which is the distance estimation in general metrics. So Alice and Bob get a pair of inputs from some metric space with the promise that either the distance is far, some parameter t, or close, and you want to prove an information complexity lower bound for this problem. So this is what led us to consider these types of inequalities. This is also a negative type inequality, but holds only for this thing, particular metric spaces, and it's referred to as a Poincaré type inequality. So it doesn't hold all the time, so you have to derive one such thing. So the definition is as follows. You have a particular distribution eta 0 on closed instances. another distribution eta 1 on far instances, and you have a parameter lambda. And we say that a Poincare inequality holds for this metric space if no matter how you embed M into L2. So this is what I mean by labeling the points M by the induced embedding in L2. If the following inequality holds, that the expected squared Euclidean distance under this embedding for close instances is at least lambda times the corresponding thing for far instances. And this inequality sort of seems to be going the wrong way counterintuitively because it's putting close things on the bigger side. But that's precisely the point, because this is being used to prove non-embeddability. So you want to say in some sense that even the close points accumulate enough distance under the embedding so that you cannot hope to keep the far points farther apart under this embedding. Okay, so examples of such this thing. So on the line metric, this is just points, integer points 0 through d. And this just comes from applying Cauchy-Schwarz, that you look at the close ones are the ones that are adjacent on the integer line from 0 through d, and the only farthest point is 0 and m, and you get 1 over d as the lambda, the constant, the Poincare constant. By the way, I should mention that that particular quantity is actually computable for at least these graph metrics through there's a well-known connection, well-known SDP that actually can compute it. And I can sort of jump ahead and say that that SDP is the one that actually for graphs computes the spectral gap, and therefore for expanders you get a Poincare inequality with lambda equal to the normalized spectral gap. On the Hamming cube, this is the one that I mentioned earlier, that you can prove such an inequality just through simple arguments, taking the short diagonals lemma and doing an induction type argument. A more sort of involved type of inequality is the one proved by by Andoni and Rovi Kraut-Gammer, who did this for edit distances. And I'm sure there are a lot more. I'm just not listed all of them here. So I hope that these things will play a role in the kinds of communication complexity bounds we want to prove. So the theorem that we showed was that, in fact, you can prove an information complexity lower bound of lambda. There's one such version that we proved. I mean, there are some small variants to this. So, right, at the heart of this particular theorem, after you go through all the standard machinery of the direct sum theorem, is just a very simple negative type inequality for distances induced by communication protocols, and that is the following. So it is this type of inequality. So let me parse this for you. So we are going to pick a pair of inputs to Alice and Bob according to eta 0. This is the one where the Poincare inequality says they are close. And so you're looking at, in one case, giving U to Alice and U to Bob, and in the other case, giving U to Alice and V to Bob. So these are pairs of inputs, but nevertheless, they are still close because either the distance is 0 or because it was picked from eta 0, they are close, right? On the other side, we are looking at UV picked according to eta 1. This is the far pair. And in this case, we are measuring the distance between UU and UV. Well, this distance is still 0, but UV is picked according to the far distribution. So these represent, in some sense, far things in this communication problem. Okay? And what we show is that this kind of inequality holds for those embeddings. There's a lot of things buried in here. And I say the distance between this and this, I'm fixing a particular protocol, and I'm looking at the corresponding transcript wave function, and I'm looking at the L2 distance defined by that particular protocol. So this is a protocol-specific inequality, and it works only for communication protocols. Okay, so let me just prove this. The proof is just 3 lines, and then I have just one more slide after that. Okay. So, right. So you start with something which looks slightly different than what I had in the earlier slide, because in the earlier slide I have just one expression here. Now I'm going to put 2 expressions. This is something that you can do by symmetrization, I won't get into the details. So you have u, u, uv, that was one of those terms there, but I'm also adding uv and vv, so where the first coordinate also changed. Right? Okay, so now, so yeah, I have an animation going on the right side. You can see what's happening. So you just first apply this weak triangle inequality, which means that I can replace the two red edges by this red edge. And I want you to follow as we go along as to where we are looking at close pairs and far pairs. So far we are only looking at close pairs. This is all close. UV is picked from eta 0. And still UU to VV, it's still two close pairs. And now here's the thing I can do is that now I can think, oh, okay, so I do have a Poincare type inequality where I associate u comma u as the embedding of the point u, okay, and v comma v as the embedding of the point v. This is sort of similar to, I think, Hartmut's talk, in which he was looking at the diagonal points. So this is doing some similar thing. Maybe there's some superficial similarity or maybe something deeper, I don't know. When I saw your talk, I was sort of struck by it. So yeah, so we're just looking at the diagonal points, and now you can say, oh, each of this I can think of as the embedding of the point u, right? And therefore I can apply the Poincare type inequality to move. So there's, if you look at these things, they should be exactly the same, except that now from eta 0 I move to eta 1, from close to far. And of course I have to put this constant lambda in for the Poincare type inequality. Okay, so that's now this edge. Now this is wrong. I mean, I made a mistake, because this still should be a red edge. Why? Because we have moved no doubt from eta 0 to eta 1, but look at the 2 points. They're still of distance 0, right? So the two pairs of inputs being compared are really still close instances, right? And I mean, understandably, this shouldn't have worked by this point, because I have not used any property of communication protocols. I've just used Poincare type inequality, triangle inequality, and yeah, indeed, what you need to do is apply this Z lemma that says that I can lower bound this diagonal by the two horizontal edges here. And at this point, you see that you achieved what you wanted, which is that this pair UU and UV represents a close pair and a far pair, because UV is coming from eta 1. And a similar thing there. So, and then you have to do some symmetrization at the end, so to get the inequality that I claimed earlier. So that is it, basically. Okay. So basically this negative type inequality is really at the heart of the proof for metrics that gives you all the tight lower bounds for some streaming problems. Okay. So I want to conclude with there's one more slide after this, but let me say that you can also derive some kind of negative type inequality for k-player number in hand protocols. I should have mentioned that. So let me parse this notation for you. So let k be a power of 2. So there are 2 to the r players. And I want to look at the following setting where the inputs can be identified with points on the Hamming cube of dimension d. So you need to be able to map your inputs into points on the Hamming. I mean, they can actually be the inputs themselves. That, indeed, for the k parties, each player gets a 0, or exactly one of them gets a 1, or they can get anything, right? There is nothing about promise, nothing here. This is like any regular protocol, but it also applies to other situations where you have other sets of inputs, but you can do this mapping. So in that case, it says that basically if I think of these as close pairs because they're corresponding to edges in the Hamming cube, and these are as far one single far pair, then I get an inequality of this type. So this constant C is some constant, and it turns out to be interestingly related to something that Euler studied in the context of integer partitions. It's called the digital search tree constant. So, I mean, how often do you come up with Euler in communication protocols? So I'm in good territory here. So that's cool. Okay, so that's all basically I had to say. Let me conclude that you can usually take these information complexity arguments and via direct sum argument prove tight communication complexity lower bounds for different problems. But that direct sum argument uses chain rule. But interestingly, in all these applications, you can replace this chain rule also by appropriate distances in the Euclidean space. When you're doing some kind of tensorization, but you can live entirely in the geometry induced by these, geometry of distances induced by communication protocols. It's a little, maybe the chain rule thing looks nicer, but in particular, you have to extend pairwise distances, which is what I have been dealing with, to looking at distances between collections of points. And this might seem like an artifact that I introduced for just because I wanted to live in this space and not use chain rule. But there are other problems where I have encountered the same thing, and there it's not an issue of trying to fake chain rule by geometric structure. There's truly something going on in these other problems that I don't understand because they involve combinations of points and distances. I have to reconstruct this thing, but it seemed quite hairy that I sort of gave up. So I believe that this theory is still in its nascent stage, and it requires maybe some smarter thinking. But I hope some of you will take up on it. Thank you.
So is there something maybe that can be done in the opposite direction? So there are a lot of open problems about metric spaces. Or is it too specialized to this structure?
Right. So there is this connection that I think Alex and his co-authors have been pursuing, which is to take communication protocols and say something about metric embeddings themselves. I don't know if it goes in the direction of proving lower bounds, but it does say that you can take, so they have some new results along these lines. So, but one has to check if it's going in the direction that you are interested in.
What directions are even there?
Yeah. So there's a new paper by Alex, Roby, and Ilya, which is going to appear in Stock, which is precisely about this. And there's a nice blog post about this that Ilya has written too. It's worth looking at it.
What is the next reasonable open question to think about in this?
In this space, the thing that I have been stuck on, and I guess we have all been stuck on, including in earlier discussions with you, is the AND/OR tree. So we know that the decision tree lower bound for that problem is tight. It's a balanced tree of log n depth with n leaves with alternating levels of and or. So we know the exact decision tree complexity of this problem. But if you just put label the leaves by x1, y1, x2, y2, and so on, the best lower bound that we know is, I think, root n, just by the fact that you can have an instance of set disjoiners in it on root n inputs. But we don't know anything better than that. And it is in this context that when we were trying to do information complexity that we ran into some really hairy measures that we didn't know how to bound. So that would be one thing. The second thing I would mention is nothing is known about the kinds of problems where you have a fork-like structure, right? You solve some problem, even the classic fork problem in the Karchmer-Wigderson game, you solve some problem, and based on that, you either go left or right. It's some kind of binary search thing. And that has to do with more about enhancing, I think, direct sum to deal with these types of things as to when you have conditionals involved. So I don't know if that can be tackled directly through geometry, but certainly direct sum arguments didn't seem to give us anything. We tried, but